Hello everybody, my name is Dmitry Baranov, and today I'll be talking to you about barriers and opportunities in applications of assemblies of perovskite nanocrystals. So what are these assemblies I'll be talking about? These assemblies are close-packed nanocrystal solids, often called superlattices, supercrystals, colloidal crystals, or mesostructures in the literature, that contain closely packed nanocrystals with a long-range order. For example, here shown optical microscopy image of cesium-lead bromide nanocube superlattices assembled on top of the silicon substrate. Given that these assemblies are made from perovskite nanocrystals, it's natural that their optical properties are tunable. For example, here I show that nowadays it's possible to fabricate superlattices blue emitting, cyan emitting, not shown, and also extending all the way to the red. For example, by changing composition from pure bromide, that is green emissive, and adding different amounts of iodide and tuning the emission towards yellow, orange, and red. Why are these superlattices different from the ones made from cadmium selenide or lead sulfide, for example? Turns out that they are very well-ordered nanocrystal solids, and they display only angstroms of disorder. How do we know that? By taking their wide-angle X-ray diffraction patterns, we observe that this 15 degrees peak arising from reflections of the orthorhombic perovskite crystal structure contains a sharp substructure peaks arising from the superlattice periodicity. So it's a secondary interference of X-rays diffracted by individual nanocrystals that produces this fine structure. And based on this observation, we developed a multi-layer diffraction method for quantitatively fitting them and extracting interparticle spacing, nanocrystal size, and their fluctuations. To learn more about it and how this method works, please attend the presentation by Stefano Tosa tomorrow morning, as well as his poster. So what are these superlattices good for? I'll discuss three possible applications. Number one, it's micro LEDs. Since they're naturally of micron dimensions, these superlattices are suitable for producing high resolution density displays with a wide color gamut, taking advantage also of the narrow, pure emission of perovskite nanocrystals. As well, I would argue that the superlattices are suitable as miniature coherent light sources for fabrication of photonics integrated circuits. Here's shown an example not on a superlattice, but on a single quantum dot emitter. And I think it's possible to extend this type of circuitry into the colloidal assemblies. And lastly, artificial photosynthesis looks promising because of existence of long-range and directed energy transfer, as shown recently by us and also in this published paper from Molecular Foundry. However, there are challenges associated with adapting self-assembly and superlattices towards these applications. So the first challenge is how to integrate them with the nanofabrication process. Since common techniques to produce superlattices are by slow solvent evaporation or by oversaturation of nanocrystal dispersion, that doesn't exactly go well with the deterministic placement onto circuitry as required in electronics. So there's a need for assembly techniques compatible with nanofabrication. And one solution or a few solutions could be deposition from inert media, such as from perfluorinated solvents. And for instance, oil-in-oil microemulsion reported by a Scholl group earlier this year shows that superlattices of more or less regular and controlled size can be produced, as well as templated assemblies, as demonstrated in this recent work by Polovarapu, Feldman, and Liz Marzan. The second challenge is photostability. So the tunability of the emission spectrum of superlattices, for example, by mixing iodide to bromide, comes with a cost. There is a halide photochemistry under high photon excitation flux, and that can be illustrated in this microscopy video of initially an orangish superlattice that gradually turns bright green when exposed to intense excitation photon flux. That is because there is an iodide photooxidation and sublimation happening, transforming superlights into pure bromide. So how to prevent this type of processes? And here I would argue we can learn a lot from the community of mixed halide thin film perovskite researchers, where tricks like mixed A-side cations have been used, and as recently reported by Kamat group, for example, a pinch of salt, a small amount of chloride can enhance the activation energy barrier for halide migration, thus preventing halide segregation. Next challenge is that of aging. Because starting nanocrystals are capped with a labile surface ligands, such as alkylammonium oleate, the superlattices, where nanocrystals are closely packed, are metastable towards coalescence. So what happens is that if you wait for several days, the initially small nanocubes start merging into larger domains. That means that you produce different band gaps in your material, and although you create a directed energy transfer, but you also change emission spectra significantly. For example, as we observed at low temperature at 4 Kelvin, fresh superlattice peak, a bit higher in energy than 2.4 electron volts, narrows and dramatically shifts to the red, almost by 100 MeV after a week of superlattices, the same superlattice being kept under vacuum at room temperature. So how to prevent aging? Couple solutions are possible, and they all aimed at modifying the surface chemistry. For example, by inorganic capping or by zwitterions, as has been demonstrated and developed by the Kovalenko group at ETH, as well as by employing mixed ligand shells. In this nice work from the Garnett group, they added thiocyanide ligands that partially replaced native carboxylates and produced stable monolayers of self-assembled nanocubes. So here I will I'm showing the references I mentioned throughout this presentation, so you can pause and take a screenshot if you would like to check them out later. And with the permission from organizers, I would like to advertise News in Nanocrystals seminar. It's a students and postdocs run Zoominar, all things about nanocrystals. And its format is a university seminar-like event, which is free to attend. And we hope to mediate pandemic shutdown of the academic exchange and collaboration. Our next speaker next week will be Professor Vanessa Wood from ETH Zurich. So please sign up and apply to give a talk at our website and follow us on Twitter for the latest updates. So with that, I would like to conclude and thank Mana Group at IIT, as well as collaborators, Stan Group at the Foundry, Kuna Group at Notre Dame, Sanvita Group at CNR, and Giannini Group at CNR Institute of Crystallography. Also, I would like to thank the funding sources for this work. That is Marie Curie Fellowship Retain and IIT Nanochemistry Funds. And I'd like to thank organizers for this opportunity to present, and thank you for your attention. I'll be happy to answer your questions. Thank you.